Okay, so linear regression is one of the more common procedures that we're going to do in science in general. It's sort of the default first thing that folks do when they're interested in looking at relationships between variables. And I'm sure I'd be shocked if you guys haven't done it before. All right, and the basic idea of linear regression is that we've got a, I gotta align my screen in my notebook here. It's gonna be hard. So the idea behind linear regression is that we've got two variables, and what we call an independent variable, we'll call that X, and then a response variable or dependent variable we'll call Y. All right, and the basic idea is that we make a bunch of measurements of X and Y, and we get a bunch of data points that are scattered around. And if we're lucky, they follow some kind of linear trend such that as X gets bigger, Y gets bigger. Or it could be the other way around, as X gets bigger, Y gets smaller. This is the same thing, but the idea is that they co-vary, right? So as X gets bigger, something happens to Y, and that happens in a linear fashion. All right, so what we're after is some line that gives us the best estimate of the data. So if you've done this in Excel, you hit give me a linear regression line and you get some line that sort of goes through the data. And what this line does is it says, okay, I've got a value here of X. We'll call this X sub I. And my regression line gives me a value, a estimated value. Y sub I, and we'll call this Y hat. And the hat is because it's estimated. All right. And this guy up here is the real observed value. So there's some difference between the estimated value and the observed value, some error in the model here. And we'll call that, oh, that's not what I want. That error is not 3. That error is called, we'll call it epsilon sub I. And that is the error between the true value and our estimated value right here. All right, so what we're after, what we have here is a series of values where Y sub I, the true value, is equal to the equation for our line. What's the equation for a line? Can anybody rattle it off the top of their head? Mx plus b. Thank you, Wendell. M times x sub I plus b. That's the equation for my blue line here. And then I've got some random error I've added to it, plus E sub I. all right, this error. And this error, in a perfect world, this error is a random variable. This is noise in our instrument, some kind of random deviation of the linear relationship. But if we were to collect this data 1,000 times, we would guess that this error would be different each time because it's just a random sampling. So the error is a random variable. And at the end of the day, what linear regression does, the idea behind linear regression is to find the line. The process of linear regression is finding the line, finding M and B such that the total amount of error is at a minimum. That's the basic idea behind linear regression. We're just trying to minimize the errors or the differences between these lines and our regression line. So in statistics speak, we say linear regression seeks to minimize the variance, all right, of the error of E. And we'll talk more about what this means, but variance, if we think about a bell curve, all right, standard bell curve, it's got an average, and the spread of the bell curve is the variance, how wide the bell curve is. And so what we're after is some model that our best model will have the narrowest amount of error or error variance. Okay, so that's at its heart, all we're trying to do is minimize the difference between these dots in our line. And when we do that, we minimize the variance of the error. Okay, so the first thing we do when we're going to do linear regression is we're going to think about how these two variables, y and x, co-vary. So do they have a strong linear relationship, or do they have a weak linear relationship? And we characterize that with the correlation coefficient. So if you've played with Excel or done this before, in Excel, it gets called R squared, all right? Which is actually the square of the correlation coefficient. But the correlation coefficient is basically just a ratio of how much these two co-vary, all right? So how big or strong the linear relationship is to the total variance of the data, all right? So what is the total spread of the data, and what is the relationship? It's the ratio of the relationship between the data to the spread of the data. So correlation coefficient R relates the covariance of the data, or the relationship between the two, to the total variance in X and Y. All right, how strong is the relationship between them compared to how much just do X and Y vary? All right, and it has a pretty simple definition and calculation. It's the covariance of X and Y over the standard deviation of X, standard deviation of Y. And I can write this out in non-statistics terms, something we can easily calculate in Python, as the sum for all data points of X sub I minus the average of X times Y sub I over Y bar, or the average of Y. So this up here, this is just if X is a lot bigger than the average of X and Y is a lot bigger than the average of X, then they covary, they have a strong covariance. All right, so this just measures the tendency of when X is big, is Y also big, normalized to their average values. And at the bottom, it's the sum of X sub I minus X bar. This is the standard deviation of X from its average. So this is the spread of X around the average. And this is the spread of Y around the average. Sum. Oh, I've got an extra bar in here that doesn't make sense. Of Y minus Y bar. All right, so this is how we calculate the correlation coefficient. And if you've used the statistical software in the past, this is just what it's doing behind the scene. All right.
Question.
Yeah.
So are we using absolute values?
No.
So can X sub I potentially be smaller than the mean?
It can totally be smaller than the mean. But you do bring up a really good point, Maeve.
We need a square.
We need a square here. Thank you, Maeve. So this is the correlation coefficient. You'll also hear this called the Pearson correlation coefficient. And one of the nice things about the correlation coefficient is there's another value that we report a lot. This is called R squared. And this is really just equal to the Pearson correlation coefficient squared, all right, or the square of this guy. And R squared gives us a measure of the amount of the variance in the data explained by this linear relationship. So R squared is the fraction of variance in the data explained by our linear model. All right, so when r squared equals to 1, that means 100% of the variance in the data is explained by this straight line. So my data has to be a straight line. All right, when r squared equals to 0.5, 50% of the variance in the data is explained by this linear variation. So that's the point at which only half of the variance is explained by our linear relationship.
And the variance, what's the variance?
Good question. Yeah, it is, well, let's talk about what the variance is. The variance is a measure I mean, it in many respects, it is what it sounds like. It's the variability in the data. But let's say we've got a bell-shaped curve. All right, so this is the probability or we looked at them as histograms, say of snow distribution, all right? And so this is the most probable value, and these are less probable values. The variance is a measure of the spread or how wide this curve is. And all it really is, Wendell, is just like what ranges do these range over? And can the straight line explain, can the straight line explain the data very well, or does it not explain the data very well? So at the end of the day, what the correlation coefficient tells us is how much of the difference between X and Y is explained. How much of the relationship between X and Y is explained by a straight line? Okay. So correlation coefficient just gives us an idea of how strong that linear relationship is between the data. If it's a number close to 1, if the correlation coefficient squared is close to 1, 100% of our data or a lot of our data is explained by the straight line. If the correlation coefficient starts to get close to 0, that means there's no linear relationship. All right. So what we want to do in general, we'll get a data set. We'll have X, we'll have Y. All right. We'll have a series of data points of X and Y. We can calculate R using this equation right here. But we also want to calculate M and B. All right. The best fit model and the best fit slope and intercept so that we reduce the error to the minimum, the absolute minimum that we can. So we can estimate M and B to give the minimum error. All right, so these are equations that can be derived, but the slope, you might expect that the slope, M, is related to the covariance between these two, or the correlation coefficient. So when there is no linear relationship between the data, there's a zero slope. All right, when there's a strong relationship with the data, then there's R is 1 or something like that. And then there's a very strong linear relationship with the data. So M can be calculated as the correlation coefficient, Rxy, times the standard deviation of the Y over the standard deviation of the X. All right, so this is our second equation that we'll use today. And it just says I can calculate the slope. Once I calculate my correlation coefficient, I can then easily calculate the slope of my best fit line using this equation. Now, I'm just giving you this equation. There's a lot of really cool math to show that this is the minimum error. And I'm sparing you from it so we can play with it in Python. All right. But suffice it to say, this M gives us the minimum amount of error. All right, so we've got M. Now we need to estimate the intercept. And the intercept basically relates the average X value to average Y. All right, and the equation for B is B is equal to the average Y value minus the slope that we got up here times the average X value. So this is our best fit intercept. Okay. So what we're going to do today is just start playing with, we're going to make some synthetic data where we know the true relationship. We'll add some error to it. And then we'll see how our M and B estimated with these equations compare to the true values of M and B, and just see how the amount of error we have in our data affects our estimate. All right. Then on Thursday, we'll start to quantify our uncertainty in our estimate and show that our uncertainty, if we properly quantify our uncertainty, then we can calculate not only our best fit, but what our best fit values might actually be. So at any rate, let's now shift gears and open up Spider. The main equations we're going to play with today are this Rxy, M, and B. So open up Spider.
Do we always open up Spider by opening up the PowerPoint?
You know, nothing we're going to do. So it doesn't hurt. It doesn't hurt. We're only going to use simple libraries today that you don't need our fancy environment for. So today it doesn't matter. You can just click on Spider. We're not using any fancy GIS libraries today. Oh, actually, I can open up Spider on this machine. Okay, so open up a folder and then we'll create a new script. Linear regression. All right, let's see if I can make this one zoom in. If I can't, oh, I can. What about this one? Okay, so we're going to import some libraries. Today, all we're going to use, we will import NumPy. And we'll import matplotlib.pyplot. So the first thing we're going to do is just make a random. We're gonna start off with a our independent variable. All right. So this one is something we know. So we will use linspace to do this. So let's do a couple things. First of all, let's think about how many samples we have. Let's make it 200 samples. Or we'll do 100. It doesn't matter. We need to think about a starting spot. So let's have this start at 10. And a stopping spot, an ending spot. So let's have it stop at, I don't know, 200. So this is the number of data points. Starting point and ending point. All right, so I'm going to create this array of X values using linspace. All right, linspace wants a starting point. So XSS wants an ending point. XXE, and it wants a number of points. So we'll make that N. All right, so we're going to make this is a really common thing to do anytime you're computing, is make some synthetic data. And the nice thing about making synthetic data is that you know what the true data is. You add some random error to it, you can see how that error affects your calculations. So first thing we'll do is create a known y, where we know what the real value of the slope is, and we know what the real value of the intercept is. So let's make a real slope, m sub r, and we'll make our real slope, I don't know, we'll make it equal to 2. And you can play around with all these later. All right, so And we'll make a real intercept. I don't know, what do you want it to be, Kip? 3. That's one more than 2. Okay. So now I can make sort of a real y vector, YYR. And that is just mx times b. So me times xx plus, oh, I did this, br. All right. Tell me I got an error here. Oh. Man, Spider. It's catching my bugs. All right, I'm gonna run this really quick. And let's just look what we got. We have XX. It's an array of floats. Its length is 100. That's good. If I look at the values, it starts at 10 and starts moving up. All right. I got YYR. That's an array of floats. Length 10. It starts at 23 and then starts moving up. All right, so this is my real data with no noise. How about this? This is my not real, because there is no real data with noise. We'll call this true. My true data, not tour. All right, so now let's make some noise. I'm into it. Okay. We're going to do this in a way that we can adjust the level of noise. So let's create this EFAC, and I'll show you what it's going to do. But it's some factor of the average of Y. So let's make it be 10% of the, or no, we'll make it 20% to start. So 0.2. Times YYR dot mean. All right, so 20% of average Y. It's noise. All right, so now we're gonna use a very, very useful function. np.random. All right, .rand n. So numpy.random is like a subset of numpy that's all about generating random numbers and random variables. All right, and it's super, super useful. I use this rand n all the time, and a lot of times for stuff like this, creating synthetic data sets. So what rand n does is it creates an array of random numbers, whatever length we want it to be. So we want it to be the same length as Y. So we can just put length YYR. All right, so this is, we'll see, but this is going to create an array of random numbers taken from a Gaussian distribution, all right, with a mean of 0 and a standard deviation of 1. In fact, let's get some help on rand n. What do I hit? Control I. I don't know if it'll work on my Mac. Boom. I don't want it for. I want it for random. Okay, return a sample or samples from the standard normal distribution. So the standard normal distribution means a standard Gaussian distribution, the classic bell-shaped curve you guys are used to seeing with an average of 0 and a standard deviation of 1. What I want to do now is what was really nice about the standard distribution is I can easily change it to have any I can easily change it to have any standard deviation I want by just multiplying this by the standard deviation I want. So if I want the standard deviation, for example, to be 20% of the average of Y, then I can just multiply this by EFAC. All right, so now I'll have, this is a noise with 0 mean and standard deviation of EFAC. All right, so now I'm going to make the noisy data. If we just go back to our original idea, our data is equal to our linear slope, our line, plus the error. So that's all we're going to do. We're just going to take the line and add the error. We've already got the line right here, so we just add the error to it. So YY, the noisy data, is equal to YYR plus E. Okay. And now let's just take a look. Let's plot this up and take a look at our data, and we can play around a little bit with EFAC and see what it does. So we'll plot the data. Let's see what this looks like. Hmm. That's horrible to see. Ugh. That's too big. Okay, so here's what my data looks like right now. Not a huge fan of this window size, but. All right, so you can see there's a linear relationship, all right, but there's a fair amount of scatter in the data. All right, and now we can do things like play with the error factor. So it's worth doing that a little bit. Like, let's see what happens if I change this to, I don't know, 0.1. I have much narrower band of error around my line. You can change it. Let's change it to 0.5. All right, a lot of error. There's still a line there, but it's starting to be harder to distinguish what that line looks like. Okay, so we've created a synthetic noisy data. Let's keep it at 20% for now. So I'm going to go back and keep it at 20%. All right. Let's estimate B and M. All right. I'm not going to lead you by the hand here. The equations are, first we need to calculate the correlation coefficient. Then we need to calculate M, and then we need to calculate B. Actually, I'll help you calculate the correlation coefficient because I want to show you how easy this equation is in Python. All right. Let's just calculate some useful things that we're going to use a lot. So we're going to use the average of X a lot. So X bar, XX dot mean. We'll use the average of Y. We're going to use the standard deviation of X and Y. All right, so these are just things we're going to use a lot. And I don't want to type out XX dot mean and YY dot mean every time. You could, there's not that much more typing, but.
You did an XX to Y bar.
Oh, that'd be a bug right there. Thanks, Wendell. We'd get all kinds of weird answers and I'd be like, what is happening? All right, now. RXY. All right, let's look at it. The first one is the sum of X minus X bar times Y minus Y bar. All right, so that's the top. NP dot sum. All right, and then the first thing in the sum was all right, so right here, I'm really taking advantage of the fact that Python by default will do everything element wise. So it's gonna automatically take every element in Y and subtract it and subtract the mean from it. And that's gonna be a vector. And then it's gonna take every element in X and subtract the mean from it. And that's gonna be a vector. Then it's gonna multiply those two vectors and then it's gonna add them up. So that whole big long thing, I could have had to write a for loop that looped through every vector and added them and did all that. It's one line in Python. Easy. Okay, now let's do the next line. Divided by, and I'm gonna see if I can take this down. Let's see if I can take this down to the next line. Divided by NP dot, well, we're going to want to put parentheses, NP dot square root I'm going to go over these parentheses with you here in a sec. All right, so the first one is the square root of X minus X bar squared. And they told me I had to remember this squared, or else I'd have hell. I did. Trying to take square root of negative numbers, imaginary things happen. So thanks, Maeve. All right. Times. I need to do NP dot square root y minus y bar squared. And then, yeah, that's all the second line. So one of the nice things, this syntax highlighting allows you to look at the different parentheses and make sure they line up where you want them to line up. So I want this outer one to be everything that's in the denominator. That's the two square roots. And then each square root has this quantity squared. And then each interior one is just making sure I do the subtraction before I square it. And let's go ahead and print. I'm gonna give you guys some fancy printing here.
Do you need NP dot sum in the denominator?
Let's check that. We might, Maeve. You guys are finding bugs for me all over the place today. I just need you watching me code all the time. This is a fancy printing thing I'm going to show you. I'm just kicking down knowledge, but let's make sure our that we have NP dot sum. Let's see, am I doing that right? Square root of the sum, yep. Square root of the sum of y minus y bar squared. All right, so Wendell's asking about this. This is a different kind of printing. So this percent thing says, look for a percent out here, take the variable that's on the other side of the percent and put it in here. And the 0.3f tells it the style to print it. So this is going to have 3 decimals place and f is a float. All right, so this says print. What this says is print RXY as a 3 decimal float right here. Or actually it's going to print RXY squared. Here it's going to take RXY and print it as a 3 decimal float. So the correlation coefficient is 0.95. The R squared is 0.9. All right, this says that 90% of the relationship between X and Y is explained by our straight line. Good. Let's play around with the error and see what happens. So I had this up to 50% standard deviation. Let's save it and run it. Now my R squared is like 0.5. So when I add a lot more error, now it's saying only about 50, little over 50% of my relationship between those two data is explained by my straight line. I made it 80%. If my variance is 80%, all of a sudden you see the slope of this line is getting really hard to see. My R squared is 0.35. So less than half of the data is explained by the straight line. So play around with this. This is good intuition forming. If I make it 0, I'm going to get a perfectly straight line and my R squared is 1. So if my error is 0, I get a perfectly straight line and I get an R squared of 1. If my error is 100% of the data, make it 300%. All of a sudden now the error is a lot stronger than the linear relationship and have an R squared close to 0.07. So like almost 0. Yep. All right, so play around with that a little bit. Take a few minutes, play around with this and get a feel for when I add more error to the data, what does that do to my R squared? And if you got bugs, I'm happy to come help you. Kip's got bugs.
All right, what line? Let's see. Let's see what is RX1. It's the float somewhere in here. You need a sum right here. You might need to add parentheses. Here, you want to sum this with. Yeah, I think.
All right, who else got bugs?
I got something.
All right,
really
I'll be there in a
upsetting going
second.
on.
Right.
Whoa, that's a big number.
Oh, I'm getting those.
For the R squared.
Yeah.
Where did I sum this with?
Yes, I get it.
Yeah, it's probably a. It's in the equation.
That's not.
Well, right now. It's
Oh,
okay. I think it matters. Okay, so that one is going to have its square root good. Good. Oh, okay. Square. Parentheses. There. All right, see if that fixed it. I think it should. Did it? Yeah. Good news.
Okay, mine was giving me these tragically large numbers. And then I did something worse.
All right. We got a lot of parentheses. All right, so that one looks good.
How many emails did
Yeah, there's badness there. Let's add another one. That square root is, see, this one is going all the way over the whole square root, so we know we're gonna want to do it.
where's the sheet?
It's gonna do that first, then square it, then sum it, then square root it. So it's gonna square root that, that looks good. Another one. Yeah, I don't need to. It's mostly. Try that. That looks good. I thought it was
I get rid of this.
You can get rid of them, Maeve. Let little OCD run.
Oh, yeah,
Okay.
it's very different from what you got.
Oh, like. Yeah.
It shouldn't be horribly different unless. Like, play with this error. I'll give you guys the benchmark. At,
Oh,
tw-
did you change the error? from
Yeah.
one to-
at, I'm at 3, so
Oh, okay.
0.2. At 0.2,
Perfect.
your error should be close to that. It's not going to be perfect because each time we run this, we're drawing another random sample of noise. So they shouldn't be the same. They'll probably be pretty close, but. All right. Okay, does everybody got this part running? All right, now you guys estimate B. No, what do we do first? Estimate M. All right, so it's pretty easy equation. And remember that we calculated RXY and we calculated the standard deviation of Y and the standard deviation of X already. So this is pretty much a plug and chug here. All right, the next step is to calculate B. So if you've got M calculated, calculate B. And if you need help calculating them, let me know.
Oh, you gotta have a, yeah, you have to have a star there. 'Cause otherwise it's thinking that it's an argument to the function. You're welcome. It's an error I see a lot in my code. All right, everybody got M and B?
All right. So now let's just add this to our plot. So once we have M and B, M E was equal to R X Y times S Y over S X. Why is it giving me an error? Oh, yeah. See, you guys are freaking on it now. Y bar minus ME times X bar. They shouldn't be, okay, so let's just print these out. Print. M equal to 0.3F, B equal to 0.3F. Now watch this percent MEBE. Fancy printing. All right, so what Kip said our B was supposed to be 3, right? And our slope's supposed to be 2. So it's nailing the slope pretty good. B not so good. Run it a few times, see what happens. Now B's -6. You can see the slopes changing a little bit. 2.09, -12, 2.10. So each time it's getting a little bit different of an estimate. All right. Last thing I want to do is let's go ahead and add this to the plot. So I'm actually just going to move all my plot lines down to the bottom. And I just want to, I want to plot my best fit line. So XX, and then my, well, first of all, let's calculate Y hat. So our modeled Y hat is equal to XX. It's ME times XX, MX plus BE. So plot XX, Y hat. I'm gonna make this a dashed black line. And then I'm also gonna plot the true line, right? XX, YYR. This is our true line. I'm gonna put that in blue. And I'm gonna give it a little bit of a transparency. All right, so after this, when I run this, I'm gonna get this plot. I'm gonna run this over here so we get a nice big plot that we can look at. All right, so here is, all right, the slope on this run was estimated at 1.36, the intercept at 7, all right? The slope should be 2 and the intercept should be 3. All right, here the blue is our true line and the black is our estimated line. All right, so you can see a couple things. When we add noise to the data, our estimate of the true line is not perfect. It's not going to be. We have error in our model. We don't know what the true value of the data is, and we're going to get error. So what you got a few more minutes here. So what we'll do on Thursday is we will not only calculate this black line, you've already learned to do that. What we're going to calculate are the error bars on the black line. All right, so how uncertain we can quantify what the error bars on this black line are, and then we can compare what our best estimate and the uncertainty of our estimate actually is. And if it's works out well, which when you have synthetic data, it should, then we'll see that our uncertainty will encompass the true value, even though our estimate isn't quite perfect. All right, so play around for the next couple minutes. Just play around with changing, if I make this a bigger number, 0.4, my intercept is more wrong. My slope is more wrong, and you can see bigger deviation between the estimate and the true value. If I make it really small, my slope's getting really good, even my intercept's getting better, and it's hard for me to even see the difference between the two lines. The blue line, Maeve, I added the real estimate. YYR, yeah. It's the real linear trend that should, in a perfect world, we would recover that real linear trend.
Are we turning this one in for today?
Nope, we will, yeah, we should, I didn't open anything up on Moodle. But you're gonna use this for your homework, so you'll get, not this particular example, but we'll keep working on it tomorrow or Thursday, or what is today? Tuesday, we'll have a turn in and it'll include this plus the uncertainty.
Okay, then.
See you, Boone.
Thanks, Dave.
Yeah, you're welcome.
See ya.
See you, man. Have a good day.
See you Saturday.
Saturday.